Morning, everybody. Let's see. Welcome to day 2 of Code Blue. We're happy to be presenting here today. Today we're going to be covering the topics of leveraging VMware's RPC interface for fun and profit. And we're really talking about this subject because virtualization and cloud technologies and things like this are becoming more and more important to the enterprise and to businesses for scaling and for doing things in their enterprise on the cheap. And so examining these attack surfaces, understanding how they work is vitally important to the future success of corporations. What we're going to be talking about today is this is kind of an overview. We're going to go over kind of a general architecture of VMware, how it works. We're going to go over how some of the host to guest communication actually occurs. We are going to go over the VMware RPC or remote procedure call interface, talk about how it functions, and how you go about actually triggering some of these RPC calls using your own code and by developing tools in C and C++ and Python. We're going to go over a little bit of how you would fuzz the RPC interfaces to find bugs, and then go over the art of exploitation of some of these vulnerabilities that exist in the RPC interface. So first, quick introductions. For those of you who don't know who I am, my name is Brian Gorntz. I'm the Director of Vulnerability Research inside of Trend Micro. My primary responsibility is running the Zero-Day Initiative program. The Zero-Day Initiative program is the world's largest vendor-agnostic bug bounty program. And what does this mean? We work with researchers around the world to, when they discover a zero-day vulnerability, we purchase this vulnerability off of them, and we work with the affected vendor to get it fixed. While the vendor is fixing the vulnerability, we build intelligence that goes inside of the Trend Micro products to protect them against zero-day exploitation, along with protecting them when the patch is actually being deployed. And so it gives us kind of a leg up on the attackers. I also run and organize the ever-popular Pwn2Own hacking competition, which we actually hold twice a year, once in March and once in November. For either the desktop server space or for the corresponding mobile space. So we just actually did that contest last week here in Tokyo, where we had people come out and exploit the mobile phones of Apple, Google, Samsung, and the like and bring out some really interesting exploits related to Wi-Fi exploits and baseband exploitation. I'm also the approver of payments, so if you've ever submitted to the Zero-Day Initiative program and been paid for one of your vulnerability discoveries, I'm the individual who ends up cutting the check for those exploits. In my past, I've done development work for the defense contracting world in the United States, and I've done a lot of research myself, participating in Microsoft's bounty program, where we wrote some exploits against some of the Microsoft mitigations, along with providing them recommended fixes. I've done some work on patents related to exploit mitigations, and I also do a lot of bug hunting on my own time with these individuals here on the stage with me, and I'll allow them to introduce themselves.
All right, so my name is Abdul. I'm a security researcher working with the ZDI. I've been working with the ZDI for the past 4 years, a little bit more. So I do a lot of root cause analysis, vulnerability research, fuzzing, and exploit development. I'm also the CDI case lead, so basically I'm the one who distributes. So whenever we get a case from a researcher, I distribute it to the analysts. I'm also responsible for pricing these cases, so if you guys have any questions about prices, please come talk to me about it. I'm also one of the guys who judges and prepares for Pwn2Own in March in CANSAC and at the mobile version in PACSAC. I've previously worked as a penetration tester and malware analyst at Morgan Stanley. So I pretty much went through a lot of different security roles. Some of my research that I did with ZDI is the IE exploit back in Pwn4Fun back in 2014. Basically, I was responsible for writing and discovering the vulnerability for the vendor process. I was also part of the team, along with Brian, that won the Microsoft Bounty submission. I was specifically tasked for bypassing isolated heap back then. I've also did a lot of Adobe research, like specifically in Adobe Reader. You guys can find me on Twitter if you want to follow some of my work. Jaisal.
I'm Jaisal Spellman. I also go by Wandering Glitch, and I've been with the ZDI same amount of time as Brian since 2012. Before that, I was doing like services for the security team within the Tipping Point organization that's now part of Trend Micro. I am primarily a reverse engineer, and I like vulnerability analysis and security because I really like to do things with assembly language, and security is a great place to do things with security with the assembly language. On the ZDI team, I'm the ZDI research lead, and so kind of manage and track the research projects that go on in our team. An example being Abdul and I have done research on VMware, and that's kind of why we're giving this talk, and just hypervisors in general. And then the three of us have done a lot in Adobe Reader. I personally have done a lot of reversing in Adobe Flash. And like the other two, I also am one of the guys that judges pwn-to-own competition entries. And yeah, outside of that, I've looked at the Windows kernel quite extensively. And then on the team, over the last couple of years, have become kind of the Apple guy. And so I look at all the Apple cases that come in. And I'm going to turn it over to Brian to go over VMware general architecture.
So one of the reasons that we're talking about VMware today is because we've started to see a spike in submissions into the Zero-Day Initiative program related to hypervisors. So we're looking specifically at vulnerability submissions in VMware. We've received vulnerability submissions in VirtualBox and systems like this. And so what we wanted to do is kind of expose what this attack surface looks like at a very high level and kind of drill down into a specific piece of the underlying architecture where we're finding bugs and where people outside of ZDI are also finding bugs, and talk about how you would go about triggering those vulnerabilities, how you would go about trying to find vulnerabilities in that attack surface along with the exploitation. But if we look at VMware specifically, this is a very simplified version of their architecture. And what you can see is there's a guest operating system up there, and there's a virtualized CPU that's and a lot of I/O communication happening between that and the management layer where the hypervisor sits. And you can actually interact with this I/O layer through the CPU or through libraries that interface with the CPU itself, specifically the VMware tool libraries. And there's a lot of communication that happens back and forth there. And this kind of, well, red box on the screen, it's kind of all black magic for most people. There's not a lot of understanding of what happens between these different layers, the communication that happens. And so we're trying to expose some of that for the audience today. So if we look at the host-to-guest communication, we're specifically looking at a channel that VMware labels the backdoor. Now, why does VMware call it the backdoor? I don't know, it sounds like a terrible name for an interface, because when you have backdoors in software, it usually means that there's something malicious going on, but this is what they called that interface, the backdoor channel. So if we look at the back and forth communication there's really kind of two protocols. There's a lot of commands that go back and forth over the backdoor channel, but the two protocols that we're going to look at is RPC and TCLO. RPCI is kind of back and forth communication from the guest to the host. There's a lot of communication that happens over this channel, and there's two modes of communication that exist. One which is low bandwidth and one which is high bandwidth. The low bandwidth mode is when you're sending small amount of information back and forth across the channel, and the high bandwidth obviously is when you're sending a lot more information across the channel, and it depends on how you structure the messages over this RPC interface on what exactly, which mode you're going to be using. There's TCLO, which is for host to guest communication, and as an attacker, we're not really interested in that. We're interested in communication that happens from the guest operating system to the host operating system, so that we can find some sort of vulnerability in that processing that will allow us to escape the guest and execute code on the host. Now, there's other communication channels that do exist in VMware. We're not going to talk about those. We'll probably talk about those next year at CodeBlue, and when we find some vulnerabilities in that space and kind of expose that area as well. But specifically today, we're talking about the RPC interface itself. So how does this actually work? VMware implements this interface that is called the backdoor, and how do they do it? They hijack the in and out assembly instructions in the underlying code. And they do this by setting certain flags and certain registers, and calling in or calling out allows you to communicate with the underlying hypervisor. And we'll show you how you actually do that here in a second. Like we talked about before, there's a lot of commands that can be executed in the backdoor interface. And one of those commands, the 1E command, is the RPC interface that we're actually going to be communicating with. Now, some of these commands, they allow you to extract information from the host, which we'll show you in a second, but also allow you to send back and forth communication. So things like drag and drop, shared folders, and these types of functions that you're used to experiencing in your virtual machines are actually done over this type of RPC interface. And it is enabled by default. Because it's just in and out instructions with special calls, you can actually just call these without even VMware tools or the libraries being installed on the system. So there's this misconception that as a malware analyst, if you're running your malware inside of a virtual machine, it would be impossible to detect that the virtual machine was, or the malware was running in the virtual machine without VMware tools installed. But that's not exactly the case. You can figure out using these in and out instructions to determine whether you're running in a virtual machine or not. So luckily for us, VMware open sourced some of their tools, specifically OpenVM tools on GitHub. It allows us to get an idea without having to do heavy reverse engineering what exactly is going on and what commands are available in the backdoor interface. If you look at and examine backdoor_def.h, it kind of defines the commands. And what we see here on the screen is a bunch of pound defines that define the different commands that are possible to be reached from the backdoor interface. Now, the guest can invoke some of these, and there's actually more than you think, especially over the RPC interface, which is the 1E command. Now, how would you actually invoke communication over the backdoor channel? It would look like this in assembly, and what you're doing is in EAX, you're going to load VMXH in EAX, you're going to put command-specific parameters in EBX, and you're going to put that command value into ECX, define whether you're going to use the high bandwidth or the low bandwidth mode, and then call the in instruction, and that will actually force the hypervisor to actually process that backdoor command. And we'll go over a lot more detail of how this happens in RPC in a second. Now, if you want to examine what functionality exists in the RPC part of the backdoor, there is some tools that are publicly available that allow you to trigger some of these commands so you can understand if the functionality is working, and you can test whether your scripts are actually providing you the right values. And this is in VMware Tools, rpctool.exe allows you to query those commands. It is open source and available on Open VMware Tools, and Open VMware Tools is really a goldmine of information of how to communicate back and forth over that channel. And you can see here on the screen that we're executing RPC tool. You can see vmx.capabilities.tools_is_upgradable, and it's returning a value of 1. So if you're going to be, you can kind of use this to test how your scripts are working, if they're actually working correctly by using the tools that are provided. But it also allows you to kind of trigger some of that underlying functionality that exists in VMware-VMX. You can understand what capabilities are available in VMware VMX just by reverse engineering it and simply doing a string dump of the VMware VMX code. And you can see there's a lot of different functionalities that are available over that RPC channel. So you can see here tools.capability.unity, which will come into play later. And you can also find the function handler for that corresponding RPC call by looking for similar code to what we're showing you on the screen, which will actually provide you the exact location of where some of this RPC functionality is actually being processed. Now, in summary, there is that backdoor interface. We're about to go into what that RPC interface looks like in detail. It does hijack that in and out instruction like we talked about. And what we're really looking at is for communication that's going from the guest to the host. We're going to ignore that TCLO, and we're looking specifically at the RPCI commands. And again, using Open VMware tools, we can get a really good understanding of what this interface looks like. And Jazel now is going to go over what this RPC interface looks like and how you trigger it using some of the tools that we've developed internally.
Okay, so RPC requests are sent through the backdoor channel, and guest RPC is really a protocol that sits on top of one of at least 3 different communication methods or channels. Backdoor channel is the one we're going to focus on, but guest RPC commands can also be sent over something called vSockets, which is a VMware specific type of sockets, and then also through normal sockets. For vSockets, for anyone that has ever done Windows kernel debugging on using a VM, there is a fantastic tool called Virtual KD that made kernel debugging much, much faster. And the way that functioned was by sending data over guest RPC using vSockets. And that's how they were able to make it much faster than the serial debugging. Here, though, we're going to focus on requests sent through the backdoor channel, and specifically bdoor CMD message, which is represented by hex 1e. And these guest messages are all defined in guest message def.h. And the part that we really care is message type, which is an enum. And there are different message types. For example, message type open is 0, message type send size is 1, send payload, so on and so forth. And the main thing here is if you're going to send data, you need to open and send a request saying that you're going to open and you're going to send data. If you're going to send a buffer, then you also need to send the size. Then you need to send the actual data. And then once you're done with everything, then you need to close and tell it that you're done. And so looking at what this looks like in assembly, if you pay attention just to the bold parts, you'll see message type open, and you see a move ECX 001E into ECX. If we looked at, or if you were paying attention to the previous slide, I mentioned that message type open is 0. Although we're showing 1E here, the value for the message type is actually in the upper half going into ECX. So if we look at send size, which was had a value of 1, in the bottom left, you see move ECX 1001E. And that's because it's setting the lowest bit in the highest second half to 1, and then message type close is 6.
So just want to add something here. So if you guys look, all right. So if you guys look at the first request, which is message type open, the value which is set to EBX is basically RPCI in hex and bitwise ORed with a flag. And that flag is hard-coded, which is hex A80000000. And the message type open should have that value in EBX. So if you want to start an RPCI message, that value should exist in EBX, or else it's not going to go through.
So as far as how this is implemented and how it all works, guest RPC requests are parsed within VMware-VMX or VMware-VMX.exe if you're looking at Workstation on Windows. And as a result, the functions and messages are also implemented and parsed inside VMware VMX. So if you take that binary and throw it into IDA or any disassembler, and then do a string search for guest RPC, you can then look at the cross-references to guest RPC, and right below it, you'll see a reference to a function, guest RPC funcs. If you look inside that, then you'll notice a call to this function where ICPR is sent as a string, and then another argument is a function that we've renamed to exec RPC request. ICPR is just RPCI, that string backwards. An exec RPC request is a callback that will end up getting called when we make that request. This function is responsible for handling the RPC requests, and it does so by taking it as an argument, and then does some validation primarily by making sure that the RPC function we're requesting be invoked is actually valid, so that we're not accessing something out of bounds or anything like that. It also checks to make sure we have enough permissions to execute this function. An example being copy and paste goes through this, and if you in your VM have copy and paste disabled, but it's getting a request to access the clipboard, then this is going to deny it. Assuming all the checks go through, then it'll actually execute the requested function and then return the result. Knowing that this is where the RPC requests come in, it makes for a great place to inject code so that we can try and track what all is being sent. And for this, we ended up using PyKD. PyKD is a Python module that interacts with debug engine, and so basically you can mix Python and WinDebug or KD or CDB. And the benefit here is we can set a breakpoint on exec RPC request, and we know exactly where it is within VMware VMX because of the reversing we did in the previous slide. And then we can look at the R8 register because a pointer to our request is there. And then the length of the request is in the R9 register. And so if you can, it may be hard to see in the back, but the second line of this Python is assigning underscore bytes. And it's doing that by calling PyKD's load bytes function. And it just takes whatever data is being pointed to by R8 and then reading R9's worth of bytes into that. And then it's just printing it out. And I'm going to show a quick demo of this in action. And text is going to be hard to see, but there'll be a large ASCII hex dump showing the hex bytes as well as ASCII characters. And that's about it. So an RPC request came in, and then this logged it and documented it. And we're just able to see it very quickly, which makes it easy if you want to do analysis or exploit development or anything, so you can see exactly what is being sent and being seen by the hypervisor. So now I'm going to talk about developing tools to query and kind of poke around the RPC interface. One of the issues with VMware and RPC in general is tool development because, well, when you're doing case analysis, when you're fuzzing, when you're doing exploit development, you need to be able to see inside the process and you need to be able to touch very specific parts of code. And there isn't really much to make things easier for you. Open VM tools, which was mentioned by Brian, has been released and VMware does update it frequently. However, there are some issues. Some things are implemented in vmtools.dll that aren't there and vice versa. And then there are a few cases where you have to go to pure assembly. Even if you have a wrapper around it, there's just no way around having pure assembly. If you were to try and avoid it, you could use vmtools.dll, but that also depends on that library being present on a system, which may or may not be the case specifically if you're doing exploit development. So the first take as far as developing tools around this was to write a C++ module to just import open VM tools, add it to the include directories, and then call load library on vmtools.dll, and then just call get proc address so that we get access to all the exported functions. This does work, but it does have limitations. There's some functionality that we may want to be very specific and call. And then, as I mentioned, it does require vmtools to be present on disk. So take two is using hard-coded assembly. One of the functions that is present in open vmtools but not in vmtools.dll is this backdoor in-out function, which is just raw assembly that ends up being called. And you give it this backdoor proto structure, which has input data as well as output data, and you can repeatedly call that. But downside being that you do have to implement it in pure assembly. And then in order to send RPC requests through the backdoor channel, you also have to do a little bit extra, and that's what this RPC send function also implemented in pure assembly does. It's probably a little bit hard to see, but in the first snippet of assembly, we're setting ECX to hex 1E, which is going to send the backdoor command. After that, it does a message type of open, then message type send size, it sends the data, and then finally it closes everything out. But that's not enough. Like, we can do some stuff. We also want to be able to fuzz, and we want to be able to do all this quickly. And we are definitely, at least at ZDI, very much a Python shop. We have a lot of Python code. We have a lot of Python fuzzing and analysis code. And so whenever we do anything, we want it to be in Python or accessible from Python. So we started off, and we have two different methods of interacting with it from Python. The first is using C extensions, which I'll go over in a second, and C types, which is another thing I'll go over in a second. And then our DevOps manager, Josh, he does not care for Python. He actually prefers Ruby. He was an excellent...
Unfortunately.
Yes, unfortunately. He used to be a Metasploit developer, and so he implemented similar functionality, but in Ruby using Metasploit. And we actually talked about that and released it a month and a half ago. So C extensions, they're just a shared library, a PYD file that gets shared, and it is platform specific. So you compile it for, say, Windows or Linux or Mac OS, anything. But then you can import it and then access functions that it exports as if they're from Python. And it's responsible for unboxing the variables and dealing with it, and then reboxing them to send back to Python. Here is an example of what it looks like. You define an array where you contain, where you have names of functions followed by pointers to those functions. And then you have an initialization routine that just calls PyInit module with the name of the module that you're going to use, as well as a pointer to the methods that you're exporting. And the name that you're going to use must match what you will end up using when you call it from Python. So in this case, it's RPC send with capital R, P, C, and S. And so when you import it from Python, you must match that case exactly, and you'll be able to access everything. And on the right side, you can see what that code ends up looking like. It's fairly straightforward. You call pyarg parse tuple. It takes a Python object that's a pointer to, or that's a buffer or a string or anything of that type, and it'll return back a pointer to the raw buffer as well as the size. Then we just call RPC send with those two arguments and return. If you're doing it in C types, which is a foreign function library for Python, then you can do this all in pure Python, and you don't have as much to worry about as far as portability. You can just ship this one Python file to your fuzzing VMs or exploit VMs and go from there. It makes it a little handy, but downside is that some of it's a little more involved. For example, you have this, you have to define an array of arbitrary bytes that contain the assembly you want to execute. In our case, we're using hard-coded assembly. You could make it more dynamic by using a assembler such as Capstone or anything similar. However, we know exactly what assembly we want to execute, so it makes it a little bit easier for us. At that point, you just define a function there and set that memory, that region as being executable. So for Windows, this just involves a call to virtual protect. For Linux or OS X, this would just be called to mprotect. And at that point, tell Python that there's a function there, and it takes 2 arguments, and then you just define a function to call it, kind of as a helper, and then you can just repeatedly call this over and over again, and everything will just work very, very nice and cleanly. The downside to C types over the C extension is that it will be a little bit slower, just because everything is in pure Python, but it ends up working very nicely, and as far as development goes, it's very straightforward. So now I'm going to show a quick video of what it looks like when you are running this, and this is using the C extension. So I think right now it's building it. All right, so it's built it, and then it's about to, okay, just showing that it's now built, and now it's being imported. Once it's imported, it's just going to call RPC send with disk.shrink, which is a common VMware RPC command that allows you to, from the VM, shrink the disk on the host, basically recover space and make it smaller. And you can see that after enter was hit, the VM itself started to shrink itself, and so the command successfully went from the guest to the host. And now I'm going to pass it over to Abdul to talk about fuzzing the RPC interface.
All right, so since now we have some tooling that allow us to send RPC requests, fuzzing is a little bit easier now. So I'm going to talk about 2 methods about like how to approach fuzzing, RPC fuzzing in VMware. First, there's a lot of obstacles that we have to overcome. Like typically, what do we have to run? Where does the fuzzing code has to run? Does it have to run on the host OS, guest VM, all these kind of stuff, like debugging. Should we debug the host or the VMware VMX from the host, which is, of course, we have to do test case generation. Should that be done inside the guest VM or from the host? And how do we actually manage like all these VMs? If we have, let's say, 10 VMs and we're doing some fuzzing, how do we manage all these VMs? And specifically, I'm talking about like workstation, fuzzing workstation, RPC from inside workstation. So classically, this is how it would actually look like. If we have our framework, I have my own framework written in Python. So let's say it works, it resides on the host, and it has a mutator, an agent, and basically it just spawns like a VMware workstation through VMware VMX. So typically you would manage these VMs through VM Run, which is a tool that's basically shipped with VMware Workstation. You have your mutator, your agent attaches to VMware VMX, and then your test cases are being sent back and forth. It's relatively simple, right? But this is not really ideal, and it's not really as fast as we want. So let's switch gear a little bit. So Jazel talked about the RPC sniffing tool, PyKD. So what if we actually transform that into an in-memory fuzzing tool? So we know exactly where the RPC messages are being parsed, and we're dumping these messages before they actually get parsed. So why not just modify these messages and then parse them? And basically, we're going to have something like an in-memory fuzzer. We can also modify, we can also like hook WinAFL to it, since we know exactly where that function is and the offset of that function is. So we're going to have a lot more efficient and faster fuzzing. Of course, we're going to have some obstacles, which is crash detection. That's going to be on the host, so it requires additional tooling. It's not a big deal since we're doing everything from PyKD. And recording modification, of course, that's done from inside PyKD as well. So whenever there's a modification to the packet that's being sent, it's going to be recorded, and then it's going to be sent. So this is in a nutshell how you guys can approach fuzzing like easily from VMware, or from like in two ways, in memory and the classical way. All right, so I'm going to talk a little bit about exploitation now. So specifically, I'm going to talk about use after free exploitation in VMware. I'm going to talk about a bug that we received back in March. I think it was we got that bug a week before Pwn to Own, and we believe it was a defensive submission. And by defensive submission, so usually before the contest, contestants start sending bugs to us. So hoping that it would actually dupe some of the other contestants during the contest, and then we would basically just disqualify the other contestants. So that's kind of like a defensive submission. All right. So the bug that I'm going to be talking about is a use after free and drag and drop. It's very simple to trigger. First, we have to set the DND version to 2, and then query that version, set it to 3, and then query it again. Then we're going to trigger the free. Once we do that, we can call, if we call any drag and drop function, we're going to trigger a use, and that's where the actual crash happens. So if we enable a full page heap on VMware VMX and we just trigger the POC, basically we can run these commands from RPC tool.exe, the commands here. We don't have to, it doesn't require any special tooling, so RPC tool.exe would do the job. So once we trigger the crash, it's going to look as the screenshot above. You're going to see that it's dereferencing RCX. So I personally come from like a browser exploitation background, so I did not have any idea how to exploit this use after free in VMware. So I kind of started applying the same concept of browser exploitation in the VM world. So the first thing I did is just run bang heap -p-a on RCX, and as you guys can see here, it just dumps a small stack, and it just shows that it got freed, that the object there is freed, which reflects that it's a UAF. All right, so again, from a browser exploitation mentality, so the first thing that I have to do is get the size of that object, right? So I can try to reuse that object or fill that empty spot. So what I did is I broke right before the free happened, and then again I ran bang heap -p-a, and then it dumped a stack and where it exactly got allocated. And we're specifically interested in the user size here, which is B8, which is crucial for us because we know that we have to fill that block with that specific size. So now, since we know exactly where it has been freed and where it has been allocated, the size of the object, so the next is how can we exploit the bug? How can we overwrite that freed block? So we don't have the luxury that we have in IE. We don't have JavaScript, so it's not as easy to override that object. So I started doing some reversing. It turns out that we can actually fill that object using by sending RPC requests. And for the record, the maximum number of bytes for RPC requests is hex 10,000. So once you trigger the free, then just send an RPC request with that specific size, and basically you're going to be able to override that object. I did some reversing, and I found tools capability guest temp directory, which is an RPC function that takes a string. And by sending that, like a request to that function with a specific string size, and then I was able to override that object, which was relatively easy and very stable. Right, so now we know how to override, how to claim that object, right? So next, how can we kind of move forward and exploit that vulnerability? For the record, so in order to exploit this vuln, we need a memory leak. Basically, we need like something that leaks the base of VMware VMX. So we're assuming that we have that memory leak. So I did some reversing. So basically, we're only limited to RPC functions. Again, we don't have JavaScript. We don't have that luxury. So we're just going to play by the rules, which is RPC functions. So I started reversing these RPC functions, and I stumbled across Unity window contents start. And this is a really interesting function. What it does is it grabs an RPC request and it stores it. It stores arguments of that passed to that function in a global variable. So that basically solves our problem if we have a memory leak, because we know exactly where our ROP chain can reside. If we have a memory leak, we know the offset of that global variables, and then we're good. So putting this all together. So the first step is to send a Unity request so we can store a single chain, a ROP chain, which is basically exchanges our RSP with RDI, and RDI points to our packet. And then trigger the free, reclaim it, and then once we reclaim that, we get execution. We're going to have that block pointing to the Unity packet with a single ROP chain. And then once that gets executed, it's gonna return to RDI, which is basically contains all our ROP chain. In order to make things easier, I think as of version 12.5.7, I did not check on the recent version. VMware contains an RWX region. So basically, all you have to do is just like call mem copy your payload in that region, and then return to it. It's game over. I think that's basically it. So let me show you a demo of how it works. Basically, we wrote the exploit in pure Python. And so in this specific example, we used a leak from Ponto that we got from Tencent. And the leak basically was just querying a function from high band, the backdoor, a backdoor function from using a high bandwidth channel. And then it would actually just throw a bunch of memory, and you would be able to leak VMware VMX. That's basically it. For the record, VMware VMX on Windows run in medium integrity. So if you get code execution in VMware VMX, you basically got code execution in medium integrity. So I'm going to give it turn to...
And so just to expand on it being at medium integrity, that means that if you've exploited one VM and you have 10 others, at that point you can access all the others and do whatever you want. And this function, this bug in particular, is limited to VMware Fusion and VMware Workstation. But there are other bugs that impact, say, VMware ESXi. And although we have not seen any exploit that can do that, there's potential for that, which would be devastating if you have one VM in a server cluster that gets exploited, and then you can traverse over. So just something to keep in mind.
So VMware VMX runs in medium integrity. There's a process called VMNAT. It basically runs in system. So if you guys are able to get code execution on VMNAT, you can get system on the host OS.
All right, so kind of what we've covered in this talk is, the architecture of VMware. There is a significant attack surface there that really hasn't been explored. And I would say there would be one or two good talks every year about what's going on in VMware, but there wasn't a lot of public research happening in VMware or in those hypervisors. And so when we started to kind of collaborate with some of our partners in the industry about Pwn2Own, we really wanted to see increased exploits against VMware for the purposes of disclosing those exploit techniques to the vendor to get them fixed. And I think one of the interesting stories about VMware was when we were in the disclosure room, what ends up happening in Pwn2Own is the exploit happens, they demonstrate the actual escape, and we walk into the disclosure room with VMware, and the process is we ask the vendor if they know about the bug. And if they know about the bug, then it's considered a partial win in the contest. Well, when VMware was in the room with us, when we asked them if there was a unique vulnerability, they didn't even flinch. They didn't open their laptops. They had fixed all of the security bugs that they had known about before the contest. And so everything that we were bringing to them was unique. This is different from the other vendors, right? So there's not a lot, at that time in March, there wasn't a lot of research actually going on in the space of VMware and actual disclosures happening to the vendor to get them fixed. If we go and we look at Microsoft and we look at Google, they've got their massive bug databases, and they're able to go check to see if they've received that type of submission before. And as a result, you can see that this critical code that people are relying on for isolation is not being audited as heavily as, say, the browser, right? And so this is kind of an interesting change that we'd like to push forward, is having people do research in these spaces, because there are corporations and governments out there now that are making decisions about how to isolate their environments based off of what they think to be secure platforms. And I've had a conversation recently with some people in the government who are actually thinking about using VMware, or not VMware, but hypervisors to separate classified data, right? And if you look at the type of exposure and the attack surface that's underneath some of that, that's kind of it's a scary thing, right? The ability to escape a guest operating system, get into the host, and being able to move across possibly different classification levels is something that really needs to be thought about before we start implementing some of these kind of these hypervisors and some of these techniques in the public space. Did you want to add anything there, Jez? Yeah. So, it is an interesting attack surface. There's way more going on back and forth between the guest operating system and the host operating system that needs to be researched as well. Specifically today, we talked about the RPC interface, but there's other interfaces as well there that can be looked at. There's different commands that need to be analyzed more, and we're calling on the public research community to do this research and work with the vendors to fix the vulnerabilities and partner with programs like the Zero Day Initiative, or partner with contests that expose some of these weaknesses so that they can actually implement mitigations. The vendors can implement mitigations, fix the bugs, so that we have a better and stronger isolation for everybody to use. And so with that, we'll open the floor to questions. We are the Zero Day Initiative program. We do buy vulnerabilities, we do buy exploits, we do run contests, and we pay good money for these vulnerabilities. So if you're interested in learning more about the program, please come up to us and talk to us after the contest. But other than that, we'll open the floor up for questions.